Scanning electron microscopy is one of the most useful methods for imaging solids at the nanoscale. In scanning electron microscopy, an electron beam systematically scans across the surface of a sample. Electron interactions produce a variety of signals which allow us to map out nanoscale surface structures, determine the elemental composition at the surface, as well as provide electronic structure, crystal structure, and magnetic properties of the sample. The wavelength of visible light lies between 380 and 700 nanometers. Typically, for usual SEM application, the accelerating voltage for the electron beam is set to 5 to 15 kilovolts. The corresponding wavelength of an electron can be calculated from this to be around 10 to the negative 11 meters. The Rayleigh criterion states that beta, the angular resolution, is equal to 1.22 times the wavelength and divided by the diameter of the aperture. Therefore, the resolution of the image is directly related to wavelength of the particle being used, and we can expect 4 orders of magnitude improvement in the resolving power of a scanning electron microscope over that of an optical microscope. The SEM used in the present experiment was a high-resolution field emission SEM, which is equipped with a field emission gun and enables us to resolve structures at a scale of 1 nanometer, while typical light microscopes only resolve to around 200 nanometers. The cold field emission gun typically consists of a single crystal of sharpened tungsten, which has lower energy spread than electron sources used in other SEMs. Lower energy spread means high resolution images as well as higher beam intensity, thus improving sensitivity. The tungsten crystal is submitted to a high electric field until electrons have enough energy to overcome the work-function energy barrier, at which point an electron beam shoots into the vacuum of the SEM's interior. The electron beam proceeds through a series of electromagnetic condenser lenses, which control the focal length of the electrons. We are able to manipulate the strength of these lenses in order to adjust the focus of the beam. Instead of moving the sample in parallel lines, the path of the electron beam is carefully altered by a scanning coil, which raster the electron beam over the sample surface. The electron beam then passes through a series of apertures, the diameter of which is variable, and determines the number of electrons that reach the sample. As SEM is not constrained by the diffraction limit of light, it can make use of a smaller aperture than optical microscopes. Using this equation, where T is the total depth of focus, C the circle of confusion, V the image distance, F the lens focal length, and N what is termed the lens F number equal to the focal length over the aperture diameter, it becomes clear that the total depth of focus is inversely proportional to A, the diameter of the aperture. The specimen that enters the SEM must be conductive at the surface, otherwise charge buildup may damage the specimen and distort the image. Non-conductive samples are coated with a thin layer of metal, typically gold, palladium, or platinum, by a method called sputter coating. These particular noble metals are used because they all have very small grain size, of approximately 2 nanometers, and therefore do not obscure nanometer-sized features of the specimen. In sputter deposition, the sample is placed on the anode within a contained environment, while the cathode is composed of a metal with which we are going to be coating the sample. After air molecules are removed to create a vacuum, an inert gas, such as argon, is pumped into the container. A very large potential difference is established between the anode and the cathode, causing argon glow plasma to form as argon gas is ionized to argon+. Argon cations bombard the negative metal cathode, causing an omnidirectional shower of metal atoms over the sample which lies on the anode. Now that the sample has been prepared, we can begin our investigation with scanning electron microscopy. A variety of signals are produced from the interaction of the electron beam with the sample, providing us with different tools to explore its structure and composition. The behavior of electrons, after they strike the specimen, is determined by both the elastic collisions and inelastic scattering processes between the incident electron and the atoms of the specimen. Inelastic events arise from electron-electron interactions and are responsible for the liberation of low-energy secondary electrons from the atoms. The electrons that are most commonly used by SEM are these secondary electrons, which, by convention, are defined as electrons that escape the specimen's surface with less than 50 electron volts of energy, although secondary electrons typically have energies between 2 and 5 electron volts. In order for secondary electrons to be emitted and detected by a scintillator, they must have sufficient energy to overcome the surface potential barrier. Each of the high-energy incident electrons that collides with the sample surface produces a shower of these secondary electrons. The number of secondary electrons generated is proportional to the intensity of the incident electron beam. Increasing the energy of the electron beam has the effect of increasing the penetrating power, which causes excitation of secondary electrons deeper within the sample. These, however, are usually not observed, as the free mean path is too short to allow them to escape the sample, and in practice, only secondary electrons from within 5 to 10 nanometers are observed. Beyond allowing the observation of nanoscale forms, information on texture is also provided, as rough surfaces release more electrons and appear brighter in SEM images than smooth surfaces. This effect is called relief contrast. Secondary electrons produced by SEM also provide information on surface charge, with more negatively charged regions of the sample emitting more electrons than positively charged areas, causing an effect called potential contrast. Backscattering electrons occur when high-energy electrons are incident on the relatively massive atomic nuclei, causing elastic emission of another high-energy electron. The intensity of the signal is proportional to the probability of encountering an atomic nuclei, which depends on the density of the sample. Perhaps most importantly, the change in energy of the backscattered electrons is dependent on the mass of the isotopes at the surface. Therefore, backscattered electrons can be used to determine the atomic composition. Chemical composition is observed qualitatively through changes in the brightness of the backscattered electron image, with heavier atoms appearing brighter. X-rays provide information similar to that provided by backscattered electrons. X-rays arise from the disturbance of core instead of valence electrons and provide information on elemental composition, although it's difficult to detect light earlier elements within the periodic table using X-ray. In the present experiment, we examined and compared the nanostructures of tissue paper and printing paper. From analysis of SEM images, it is clear that printing paper has made more liberal use of adhesives than tissue paper, such that plant fibers are more difficult to distinguish. In tissue paper, the plant fibers retain more three-dimensional structures and are more likely to have come loose from the surface. As the fibers on tissue paper are more loosely bound, the paper is much more porous and has greater surface area for the adhesion of water molecules. These features contribute to the greater absorbing properties of tissue paper over printing paper.